Tri-State Supply Company. We're here again at Missing Links Brewery to discuss the topic nobody wants to talk about, harmonics. We're going to talk about harmonics, and I don't mean feel. Say this is your plant and this is your power distribution transformer feeding it. And you've gotten aggressive over the years and added VFDs and other switch mode power supplies to the system to improve the production and save energy. Well, what happened to this transformer? You're getting the same transformer, but less productivity out of it and less efficiency. And that's kind of this demonstration with the beers. So what is your choice? Well, you could add another transformer and divide the power up between the two. Now the harmonics gets spread around. Or if you really want to be aggressive, you replace the whole thing and start from scratch. So that's just harmonics in a nutshell, and now we're going to get more technical.
So we put a scope on our power system, and this is what we see. This is great. That's exactly what we want to see. But that would be a plant with just linear loads in it. And what are linear loads? Induction motors, incandescent lights, resistive heaters, etc. But we've introduced drives and other switch mode power supplies into our plant, and if they get to be too great, the harmonics generator will make our sine wave look like this. Not so pretty, huh? And what are nonlinear loads? Well, in your home, TVs, computers, in your offices, fluorescent lighting, etc. In your plants, you got welders, UPS systems, DC power supplies, DC drives, and AC drives, which are one of the biggest contributors. So like we showed at the beginning of this presentation, if you have too much harmonics in your system, your transformers are going to start to overheat and become less productive and efficient, which then leads you to have to either add more distribution transformers, a bigger distribution transformer, or better yet, what if you just could reduce the harmonic content in your plant and save yourself the additional utility costs of installing bigger transformers? Well, the rule of thumb is once you start exceeding 20% of your total load capacity as nonlinear, you should start looking at the harmonics being produced and how to mitigate them. So let's go back and look at the fundamental frequency of 60 Hertz. When we induce nonlinear loads, we impose other harmonics or frequencies on top of this fundamental one. Now, rules are that even harmonics, like the second, fourth, sixth, etc., don't contribute to this, nor do any harmonic that is divisible by 3. So 3, 6, 9. So what's that leave us with? The first harmonic we need to be concerned with is the fifth harmonic. Now, harmonic is just, again, a subset of the base frequency, 60. So times 5, this is running at 300 Hertz. So the next one's going to be the seventh harmonic, which is running at 420 Hertz. And the next is the 11th harmonic, which is running at 660 Hertz. Well, when you add all these together and sum them up, what you get here is this waveform. Not the nice one we had to start with, correct? Well, in this example here, our total current is 77 amps. 70 of it is fundamental working amps. 30 harmonic current amps are being produced. Now luckily it's not just a sum of the fundamental and the harmonic. It's a vector sum. So we can be thankful of that. But if you look here at this chart, the 5th and the 7th, you can see, are the biggest contributors to the harmonic distortion. The 11th has some, 13th, and so forth, but it gets smaller as we increase in the harmonic frequency. So, why do my drives create harmonics? This little thing right here, this starts it all, the converter from AC to DC, which is needed. This is a 6-pulse diode bridge, which is basically in most 460 volt smaller PWM drives. And with that, you get the term 6-pulse, because each set of diodes make 2 pulses onto the power system. So 3-phase bridge is going to give you 6-pulse distortion on your system. So what's the big deal? What do I care about that? Well, the more the harmonic currents you produce create bigger voltage distortions in your plant, and that could lead to a lot of other issues. One of them being component overheating of transformers, generators, wires, even motors. And even though we put drives in there for pump and fan to reduce utility costs, we're sometimes reducing the power factor as well in our plant, which is counterintuitive. We're adding drives to reduce energy, but the power factors may be getting a little worse, so we're causing us to consume more energy. But you'll save more than you consume. So that's why people add drives, for cost savings. So they came out with IEEE 519, which gives us some guidelines on where does our total harmonic distortion need to be and still be within considerable operating ranges. As you can see, in hospitals and airports, they want it down to 3%. General industry, 5%. And if you have a section just dedicated to drives only, you can go up to 10%. And the current distortion limits are here as follows. Depending on your short circuit load versus your current load, those ratios will change how much allowable distortion you can have. So everybody knows the 11th commandment, right? Thou shalt not mess up thy neighbor's line voltage. And that's where we get into what you hear, the point of common coupling. The true point of common coupling, which IEEE 519 refers to, is right where the utility comes into your facility. Now, it may just come into your facility, or that utility transformer may feed several other customers. And that's one of the big reasons they want to keep that distortion under 5%, so you're not affecting your next door neighbor. In this example, once you do all the calculations, it comes out that we're at 3.6% of the voltage total harmonic distortion, and that is acceptable. Now, if you have a generator in your plant, there's a rule of thumb when you have 6-pulse drives that you need to take the load of those 6-pulse drives and multiply it by 3. So what can I do to reduce the harmonics? Well, there are several popular mitigation choices. We can put 18-pulse drives in, which, as a rule of thumb, usually you see that at 100 horsepower and up applications. We have passive filters, which are tuned to the 5th and 7th harmonic typically, because those are your biggest contributors to your overall total harmonics. We have active filters that act like noise-canceling headphones that attack all the harmonics being generated. And then you have active front ends, which is typically an active filter built right into the drive. So if you take a look at a lot of small drives we put in our plant, under 5 horsepower, typically those are known as our component style type drives, and there is no DC link in those drives, and if you just put that drive on the line, that drive can produce 80 to 120% of distortion. Sounds like a lot, right? But 5 horsepower is probably a small percentage of your overall power for the plant. So just by adding a reactor to that drive, you can reduce it down to 30 to 45%. And one thing I like to add reactors to most small drives especially is because they not only help a little bit with the harmonics, they help protect the drive itself from sags and over voltages. And sags actually affect power components even more as they put more stress as it causes more current draw. Then we have drives with DC link chokes already built in. That's our 7-class drives. So right off the bat, you're down to 30 to 40% total harmonic distortion. But if you put a reactor in front of that as well, you can knock it down to 20 to 35%. Not as big a drop as the one without a DC link, but also, again, depending on the size of the drive, a reactor can help save the drive itself from sags and over voltages, spikes, to protect that equipment. If you put a passive harmonic filter on, we can go down from about 4 to 7%. And it has a reactor built into it, so you don't have to add a reactor as well. Then the active harmonic filter, which again acts like noise-canceling headphones, can get you 3 to 6%. Multi-pulse front ends, depending on whether it's 12 or 18, can get you down to 4 to 5%. And then the active front end, which again is like the active harmonic filter, down to 3 to 5%. So if you want more details about harmonics, send me an email and I'll send you out a PowerPoint that goes over it even further. If you need help in calculating what harmonics might be in your plant now and how you might mitigate them, Rockwell has a website, and there the link is below, which brings you to their web-based simulator. So you can calculate the harmonics, you could add filters, remove filters, add linear loads, take linear loads out, etc. to help determine what and if you need to reduce harmonics in your plant. So if you don't know what's lurking in your power system, and you don't want to see issues like this popping up that you can't explain, you may want to call Tri-State Supply or AIM Services for a power system.
So that concludes this episode of Tri-State Supply on Tap, Technical Answers and Products. Stay tuned for more episodes where we'll get into depth on harmonic mitigation techniques. And again, as always, don't dilly-dally.